Okay. So today we'll talk about hyperbolic functions. Okay.
Mm, mm,
Okay. Hyperbolic functions, they are nothing but a combination of e power x kind of things. Okay. We know e power x is like this pink one, right?
Yes, sir.
Okay. E power x is like this. Now, how does e power minus x looks? E power x is this. Okay. E power minus x is this, right? You know
Mm,
this, right?
Yes, sir.
Agreed, ma. So now e power x minus e power minus x. Basically, this graph minus this graph by 2. That's what we are doing. Okay, ma?
Mm,
Sin x sin hx is hyperbolic sine is e power x minus e power minus x by 2. Okay. So now towards the right side, just observe towards the right side, e power x is tending to infinity and e power minus x is tending to 0. Okay. So this is almost nothing, right? As you go further, it's almost 0, right? So towards the right side, this graph should be equal to almost equal to e power x, right? This is
mm,
almost equal to e power x towards the right side. Agreed? This blue
mm,
one is almost equal to e power x, right?
mm,
Basically basically e power x minus e power minus this is almost equal to 0, and this should be equal to e power x by 2 because e power minus x anyway will become 0. Agreed?
Yes, sir.
And towards the left hand side, what will be dominating? The dominating will be e power minus x,
Mm,
right? So e power minus x, this part will be dominating, or in fact minus e power minus x will be dominating. E power x will become almost 0, right, towards the left. Agreed?
mm,
Okay, so e power minus x by 2 is actually this pink one, right? Towards the
mm,
left, this is dominating because this doesn't contribute anything. This is almost 0, right? So that's why sin hs graph is hyperbolic sine is something like this, something like this blue line. Agreed, ma?
mm,
Okay, so this is hyperbolic sine e power x minus e power minus x by 2. What is hyperbolic cos? E power x plus e power
mm,
x plus e
Yes.
power minus x by 2. So again, e power x and e power minus x.
Mm,
Right. Everywhere if you add, they will just add up. It is always positive. It is symmetric with respect to y-axis also. Okay, ma?
mm,
And this part, e power 0 is 1, right? E power x by 2 will be half, this point half, right? This is also this point half, this is also this point half. So both halves will together 1. Okay.
mm,
So minimum value of cos hx is actually 1. Agreed, no? We are just
mm,
adding these two graphs. Obviously, the blue one would be higher than either of the pink ones. Agreed?
mm,
Okay. Now, what is tan hx? Tan hx is this blue line by this blue line, sine by cos. Right? Now, r e power x minus e power minus x by e power x plus e power minus x. Agreed, ma?
mm,
Okay. Now, if you observe e power x minus some positive number by e power x plus some positive number. Agreed?
Yes, sir.
Okay. So, what does that mean? The denominator is always greater than 0. Sorry, the denominator is always greater than the numerator. Okay.
Mm,
Okay. So, no way e power minus this part, some positive number minus a small positive number. Right. No way this can be greater than this one. Right. But at the
mm,
same time, this part, e power minus x. Okay, e power minus x, which is this kind of graph, right? As x tends to infinity, this almost becomes 0, right? So this part, this bit becomes 0. So this ratio will get closer to 1. Agreed?
Yes, sir.
Okay, because it is getting closer to 1, that's why it is like this. Okay, ma? It is getting
Mm,
closer to 1. Similarly, when x is negative, it gets closer to minus 1. Okay? Because the numerator is always lesser than denominator when this is x is positive. That's why the graph is something like this. Okay, it gets closer to 1, it doesn't touch 1. Similarly, it gets closer to minus 1, it doesn't touch minus 1. Obviously, at 0, this is 0, numerator is 0, right?
mm,
Sin hx is 0, and cos hx is 1. Likewise, the graph is like this. Okay, now the inverse of this is cot hx. When it is 0, that should be infinity. When it is approaching 1, that should approach 1 from the other side. When it is approaching minus 1, that should approach 1 minus 1 from the other side. Okay, ma? When it is approaching 0, that should approach infinity, negative infinity. That is cot hx. Okay?
Okay, sir.
Okay. Now, what is secant hx? Secant hx is 1 by cos hx. Cos hx is this. When this is 1, secant hx also should be equal to 1. Right? When this becomes infinity, that becomes 0. Right? This is always positive. That is always positive. This is symmetric with y-axis. That also should be symmetric with respect to y-axis. Okay? Now, can you imagine how the inverse will look like? 1 by cos, hyperbolic cos will look like at 1, at 0, it should be 1. Right, at 0 it should be 1. You understood, no? So basically, what we are doing, we are trying to do 1 by of this graph. 1 by 1 is 1, 1 by infinity is 0, and this should be symmetric. Okay, ma? Secant hx. Agreed?
Yes, sir.
Okay. Now, sin hx, if you try to do 1 by sin hx, what when it is approaching 0, it should be approach positive infinity here and negative infinity on left side. Right. And when x is becoming bigger and bigger, the graph should approach 0. Right. That's what we are getting. Okay.
Hmm.
Okay. So now you know basics of all hyperbolic functions and their graphs. Okay, ma? Okay. Now domain of sin hx is R to R. Agreed? R to R. Okay. Cos hx, what is the domain? Again R to R, but range should be 1 to infinity. Okay. Range is 1 to infinity. Agreed? Tan
Yes, sir.
hx, the domain, x-axis it is everything, but y-axis it is minus 1 to 1. That's why tan hx minus 1 to 1. It doesn't touch minus 1, it doesn't touch plus 1. That's why it is open bracket. What about cot hx? Cot hx, this is also minus infinity to the range is, the domain is minus infinity to plus infinity except 0, right?
Same. Yes, sir.
Except 0. And what about the range? It is everywhere except minus 1 to 1. Okay?
Hmm.
Except minus 1 to 1. Everywhere except minus 1 to 1, minus infinity to minus 1, including union 1 to infinity. And the domain is obviously have to remove 0.
Hmm.
Okay. Secant hx, the domain is everything. The range is 0 to 1. Okay, 1 included, 0 not included. Okay? Agreed. Cosecant h, cosecant h, sin hx, whenever it is 0, we cannot take cosecant h. Rest all it is fine. Right? Everywhere it is fine. The domain you cannot include 0. And range is everything. Okay, ma?
Hmm.
Okay. Range also you cannot include 0 because y-axis it doesn't touch. Sorry, x-axis it doesn't touch. Agreed, ma?
Yes, sir.
In the y-axis, the point that is missing is actually this 0 because this also doesn't touch, this also doesn't touch. So domain, what the point that is missing is this. Okay, domain and range, what you have to remove zeros. Okay, ma?
Hmm.
Okay. Now, why these are called hyperbolic functions? Okay. Now, trigonometric functions, sin hx, sin theta, cos theta, etc. What is this point? We can depict it as cos theta, comma sin theta, right? Okay.
Hmm. Yes, sir.
R cos theta, R sin theta, we know, right? If the radius is R, then this becomes R cos theta, R sin theta. Basically, on a circle, any point we can take it as R cos theta, R sin theta, right? You know
Hmm.
the parametric form, this form, etc., right? Now, because these points cos theta, sin theta are on the circle, these functions, trigonometric functions are called circular functions. Okay?
Hmm.
Okay, at the same time, the theta also goes around and the function repeats itself, etc., etc. That's why these are called circular functions. Now, this is a parabola, right? X square minus y square equals to 1. Sorry, this is a hyperbola. Okay? X
Hmm.
square minus 1 equals to 1. You know this, right?
Yes, sir.
Now, here on the points on this, like just like we are putting cos theta, sin theta here on a circle, we can actually put hyperbolic cos hx, sin hx on this rectangular hyperbola. Okay,
Hmm.
agreed. So let
Yes.
us see, let us see how to do this. Okay. So for example, cos hx, we want to see this sin hx into cos hx, two times of that. This is sin hx, this is cos hx. If you multiply this, what you will get? You will get this one, which is nothing but sin 2hx. Sin h 2x. Okay, ma?
Hmm.
Agreed. So
Yes.
now if you want to do sin hx cos hx, basically sin h, we want to derive this one. Sin h x plus y. Okay, we want to derive this formula. What we are doing, we are taking this one and trying to multiply, right?
Yes,
This
sir.
is sin hx, cos hy, sin cos hy, and sin hy. We are just multiplying, and ultimately we are getting sin h x plus y. Okay, ma?
Yes, sir.
Okay. Now, similarly, if you replace y with minus y, what we'll get? Cos hy is anyway even function, so that's why you'll get this cos hy. Whereas sin hy is an odd function, that's why you're getting minus. Okay, ma?
Hmm.
You're getting this, no?
Yes, sir.
Okay. So now what we are trying to do is we are trying to get this cos h square minus sin h square equals to 1. Okay. This one. Okay. Cos hy. This one. If we do this expansion, right? We are just putting the definitions. Okay. Then we are
Hmm.
getting cos h x plus y. Okay.
Okay.
Okay. Similarly, if you replace y with minus y, you are getting this. Agreed?
Hmm.
Okay. Now see the interesting thing. When x becomes y, what will happen here? X equals to y. This becomes 0. This becomes what? Cos h square x minus sin h square x. Okay? When x becomes x equals to y. Basically, cos h 0. What is cos h 0? We found out it is equal to 1, right?
Yes.
Cos h 0, it is equal to 1. Basically, what we have got? Cos h square x. From this, cos h square x minus sin h square x is equal to 1. That is this first identity. Okay?
Hmm.
Okay, what this automatically means is cos hx and sin hx we can put on this graph anywhere, right? Because this graph every point is x square minus y square equals to 1. If you put x equals to cos hx, y equals to sin hx, then this will satisfy. Like cos theta sin theta we can put here, right?
Yes.
Understood. So cos ht, sin ht you can actually substitute. That's why these are called hyperbolic functions because you are putting them on hyperbolas.
Hmm.
Okay, because they'll satisfy hyperbolas. Okay, ma?
Hmm.
Okay, now we have proved this, we have proved this. How do you prove this? This is also very easy. Okay, cos instead of taking this one, we take this one x equals to y, we get cos h square x plus sin h square x. Okay, that's what we
Hmm.
have got. Okay,
Okay.
so then again sin h square x we can replace with 1 cos h square x minus 1 or something, we will get this from this. Okay, similarly cos h square if you write in terms of 1 plus sin h square, we will get this one. Okay, ma? This and this taken together, you will get this and this. Okay, now
Hmm.
divide both sides with cos h square x. This one we will get what? 1 minus tan h square x equals to secant h square x, whatever you get this one. Okay. Similarly, if we divide both this one with sin h square x, you will get this one. Okay,
Hmm. Yes,
agreed.
sir.
So basically, these are more or less similar to our regular trigonometric identities, right? Cos square plus sin square, secant square minus tan square, etc., etc. Cos 2 theta, like this. Okay.
Hmm.
So hyperbolic also we get more or less the same things. Okay. Now we have done this. Okay. So you can derive all of this, no?
Yes, sir.
You can derive all of this. Sin h, sin 2x. Basically, you're just substituting in place of y, you're putting x. Okay.
Hmm.
You can get all of this. Cos h 2x. You can derive all of this. Okay. Just do it once after the class. Okay. You should be
Hmm.
able to derive all of this.
Yes.
Okay. Now what you do on small x's, this is sin h x. This 11. Okay. 11. You have to invert this function. How do you invert this? Just try to invert this in a piece of paper and see whether you are getting the blue one or not.
Hmm. Okay, sir. Hmm. Yes, sir. You're right.
You are getting, right?
Hmm.
Okay. So now this one, you can invert this because this is always increasing. Okay.
Yes.
Now cos hx, when we have discussed about cos hx, we had this piece of the graph also, left side piece of the graph also. Okay. But to invert, we need 1 functions. Continuously increasing or decreasing kind of function will suit well, right? So that's why we removed this other part and we did inverse only for this one. Okay, we restricted the domain. Understood? In sine inverse, cos inverse, we did, right? We are
Hmm.
restricting the domain. We are not taking the entire domain because if you take the entire domain, the function is not 1 and you cannot invert that. You cannot have an inverse. So that's why we are taking from 0 to positive infinity. Okay, x greater than or equal to 0. Now, if you invert this with respect to this line, you will get this line. Okay, this is cos h inverse. Now, similarly, secant h is this. Okay, if you invert this, what you will get? You will get this one. Okay, please be convinced. You do the inverse once for all of this. Okay, ma?
Hmm.
Okay, so these are the inverse graphs. Now, similarly, tan hx, if you invert, what will happen? This one, you will get this blue line. Agreed? Are you convinced?
Hmm. Yes, sir.
You're doing inverse and don't get confused with inverse and 1 by tan hx. Both are
Hmm.
different. Okay? 1 by tan hx is cot x, cot hx. Okay? Inverse is reflection with respect to y equals to x. Okay?
Hmm.
Okay. So because here the range is between -1 and 1. Here the domain is between -1 and 1. Okay, here because the domain is minus infinity to infinity, here range is minus infinity to infinity. Okay, for cot hx, what has happened? Because the domain doesn't include 0, here range also it doesn't include 0. Okay,
Hmm.
and here range is what? Minus infinity to -1 and 1 to infinity. So here domain is also likewise. Okay, ma?
Hmm.
Cos hx, inverting this is pretty straightforward, right? There's a this y equals to x. Instead of this will just flip back again in the same way. Okay. So cos hx and that's how cos h inverse x, they kind of resemble each other. Okay, ma?
Yes, sir.
Okay. So now, so far what we have discussed about what are the definitions, what are the graphs of all hyperbolics is hyperbolic and their inverse functions. Okay. What are their domains? What are their ranges? And some basic identities. Agreed? How to derive these basic identities. Okay.
Hmm.
Okay. Now coming to the next important thing. Uh, Okay, we know the graphs. Okay. Now, when we call about these inverse functions, sine h inverse. Okay, what exactly is this function? We are calling this as sine h inverse. But sine hx we are calling in terms of e power x minus e power minus x, right? Ideally,
Hmm.
sine h inverse also we should be able to express in terms of either x, e power x, logarithm x, whatever, right?
Yes, sir.
So, what exactly is the function? Okay,
Hmm.
what exactly is the function? What we will do, sine h, we start like this. How do we calculate inverse? If sine h inverse x, we want to calculate, right? Let will
Hmm.
equate to this equals to some y. What will this become? Sine h y equals to x, right? Sine h y equals to x. What does that mean? E power y minus e power minus y by 2 equals to x, right? So
Hmm.
what does that mean? This also is 1 by e power y, right? That means e power 2y minus 1 by 2 e power y equals to x. Okay, ma?
Hmm. Yes, sir.
Okay, so x into 2 e power y minus e power 2y plus 1 or e power 2y minus 1 minus 2x into e power y. Okay, we are getting this equation, taking this and this together. Okay,
Yes, sir.
okay, now this is a quadratic equation in terms of e power y. Okay, a square minus 2ab minus b, right?
Hmm.
Agreed. So we are just solving for the roots. Minus b plus or minus under root b square minus 4ac is what we have done. Okay, e power y equals to what we have got x plus or minus under root x square plus 1. Agreed? We are
Yes, sir.
just cancelling out 2. Okay. Now, if you see e power x, e power y or e power anything is always a positive number, right?
Yes, sir.
Okay. Now, this has to be positive. If you see x and x square plus 1, which is greater? X square plus 1 should be greater.
Yes,
Okay.
sir.
First of all, x square is positive and you are adding something.
Yes,
Okay.
sir.
X square plus 1 is greater. So that's why what will happen? X minus under root x square plus 1, this will be negative. So that's why we are discarding this. Okay, we are taking e power y is positive. We are taking only the positive part of this, that is this. Basically, we are taking only the positive root. Okay, which is this. Okay, what does that mean? What is y? Y equals to ln of this thing. Agreed? Natural logarithm of this thing. But what is our y? Y is our sine h inverse x. Okay,
Hmm.
basically sine h inverse x. We depicted it like this, but in fact, what is that function? That function is actually this. Okay, ma? Okay,
Hmm.
so basically, whatever graph we are talking about, this graph is what? ln x plus under root whatever x square plus 1, right? That is this graph. Okay, ma? This is
Hmm.
actually graph of that one. Similarly, if you talk about cos h inverse x, okay? Can we just do cos h inverse and see whether you are getting this result or not?
Yes, sir. Yes, sir. You're getting.
You are getting no?
Yes,
Okay.
sir.
Here also you have to be little careful. This is greater than or equal to 1. So if are you getting two results? I think you
Yes.
are getting two results. Which one? Why are you picking which one? Which one you are picking and why are you picking that?
Sir, x greater than 1.
X is greater than 1. Why? Because
So that you won't end up getting like a negative value.
no. So you are getting this result. Okay.
Hmm.
And cos hy x equals to cos hy. You look at the function cos hy, cos hx or whatever. This the result is always greater than 1. That's why we are choosing x greater than 1. Okay, ma? This
Hmm.
yellow graph is always greater than 1, no?
Yes, sir.
Cos x hx, the range itself is greater than 1, right? So that's why we are choosing x greater than, this is greater than 1. Okay?
Hmm.
But x minus under root x square minus 1 is nothing but 1 by x plus under root x square minus 1, right?
Yes, sir.
Okay. Now, what happens to this? This is less than 1. Why? Because x is greater than 1.
Hmm.
Okay. X is cos hy. This should be greater than 1. So what will happen to this? This is actually, if you do the rationalization, what will happen? You will get this. Okay. This into multiplied by this by this, right? You are
Hmm.
getting this one. This is less than 1. Okay.
Yes, sir.
Okay. Now, e power y should be greater than or equal to 1. Why? Because y is greater than or equal to 0. Agreed.
Yes, sir.
Understood, no? That's why we are choosing this one. Agreed or not?
Yes, sir.
Okay. Why y is greater than or equal to 0? Tell me. Why we are choosing this?
Greater than 0.
Why is this one? Why is this condition? Since y greater than or equal to 0 is what we are saying, no? Why is this condition?
So that we get a proper value.
No. Because we have chosen that. Because we have chosen this one. Y is greater than or equal
Yeah, it
to.
never touches 0.
Right. Understood.
Hmm.
X equals this one and y is greater than or equal to 0. Cos h inverse x, that should be greater than or equal to 0. Because we are choosing the function like that. Because the other part, if you choose, then there will be no inverse. Okay?
Okay.
Understood, ma?
Yes.
Okay? So that's why we are choosing this. Similarly, if you try to do the inverse of this with and tell me whether you are getting this or not.
Tan H inverse, right, sir?
Yes, tan h inverse x.
And
You equate this to some y and express e power y in that terms and solve for the quadratic equation or something.
hmm. Yes, sir, I'm getting.
You're getting now?
Yes,
Okay.
sir.
So, okay. Similarly, you can do for others also.
Yep.
Cot H inverse, secant H inverse, cosecant H inverse, etc., etc. You have to be little careful when you get two results now, which one to pick. How do you choose? You choose depending on where it is positive, where it is negative, what exactly is the domain, what exactly is the range. Accordingly, you will pick. Okay, you might get two routes. Okay, when you solve this quadratic equation, so you might get two routes, but you have to be careful in picking which route. Okay, ma?
Yes, sir.
Okay, so when you are careful, you will get these results. Okay, later you finish those results. Okay, so tell me so far what we have discussed.
So we did the derivation for all of these
Ah,
functions.
okay. So all hyperbolic functions, we got the definitions, we got the identities. Okay, these are the definitions and
And
domains and ranges. These are the identities.
today, sir.
Okay, identities we have done, and then we try to do inverse of those functions. So graphs of the functions and inverse graphs of the functions, and then we established what exactly is the inverse function, not just in terms of sin h inverse, but in terms of the original function, which is logarithms and exponentials. Okay, ma?
Hmm. Okay,
Okay.
sir.
So far we have done this. Now do this thing. Sin h, you know what exactly is the function, right? This one.
Hmm.
Okay. Now try to do derivative of this. Just differentiate e power x minus e power minus x by 2 and tell me what you get. Do you get cos hx or not?
Fine, sir.
Ah, you know the definitions of these functions. Okay. Just try doing derivatives of all of this.
Okay, sir.
If you do sin hx derivative, basically what we are doing, d by dx of sin hx, which is nothing but e power x minus e power minus x by 2. We are doing derivative of this. So what you will get, half into e power x minus again e power minus x into 1, right? Into minus 1.
Yes.
What you are getting, e power x plus e power minus x by 2. Agreed? What is this function? This is again cos hx, right? So
Hmm.
that's why we are getting this one, d by dx of sin. If you use a function, it doesn't matter. We further continue, okay? Or
Yes, sir.
otherwise, if this is just x, then we'll write cos hx. Okay? If you use a function of x, this will further continue. Okay. Now
Okay.
similarly, just do derivative of this. All of this, just convince yourself whether
Hmm.
these formulas are true or not. Okay. So here what we are doing, we are again getting into trying to get the integrals using antiderivatives. Okay,
Hmm.
so because d by dx of sin hx is cos hx, obviously integral of cos hx should be sin hx. That's what we are doing. Okay, we are
Yes,
trying
sir.
to get antiderivatives from integrals from antiderivatives. Okay,
Yes, sir.
so basically now we have a lot of antiderivatives. All trigonometric functions we have, x power n kind of polynomial we have, then e power x, a power x kind of functions we have, right?
Hmm.
So basically what we are trying to do, we are trying to increase our arsenal. As many antiderivatives as we know, then it becomes easy for us. Okay.
Okay, sir. These are there in that Thomas calculus book, right, sir?
They will be there.
So I'll go through them today.
Okay, you go through them. Okay.
Yes.
But you do the derivative, it should be there in our textbook also. Is it there or not? Hyperbolic functions,
Sir, it is there.
it is a which
Not
year?
boards, I guess, but then in case it is there.
In boards it is not there, neither in first year, second year.
No, sir, as far as I remember, no. I'll go through it once.
Okay, fine, fine. Okay, so basically you please do the derivation of all of this. Okay, just convince yourself. Okay, so for example this one, tan hx, what you will do, d by dx of sin by cos. Okay, sin hx by cos hx. What is this mean? Then you will use u by v function, v du, right? Cos hx into d by dx of sin hx, which is again cos hx, right? Cos h
Hmm.
square minus sin hx into d by dx of cos hx, which is sin h square, right? By
Yes, sir.
cos hx whole square, right? But we know this identity, cos h square minus sin h square equals to 1, right? So 1 by
Yes.
cos h square, which is nothing but 1 times secant h square. Okay, ma? That's how we got this. Similarly, you can do this also. Okay, so basically these are u by v formula if you use, you will get all of this. Okay, ma?
Mm. Yes, sir.
Okay, now coming to antiderivatives. Oh, sorry, coming to inverse of this. Okay, do you remember how did we do for sine inverse x? We assume sine inverse x is some y or sine y equals to x. We did the differential, right? So
Yes, sir.
similarly, can you do for this sine h inverse u? Or this is one part of the story. Or the other part of the story is if you know f of x equals to y. Okay, that means
Mm.
f inverse uh, y equals to x or whatever. If there is a function, what we have said, if there is a function, wait, if there is a function and if f of a equals to b, f of a equals to b, okay, the
Mm.
slope of f inverse at b is equals to 1 by slope of f dash at a, right? We discussed this, right?
Yes, sir.
Okay, so the slope of f inverse x is should be equal to the slope of f at f inverse of x. Agreed?
Yes, sir.
The slope at b is equals to the slope of f at a. The slope of f at a. What is a? A is actually f inverse b, which is nothing but f inverse of x. Okay. So what we have done? F dash slope we know. If it is cos hx, what is cos hx derivative of cos h? It is sin h. Sin h of again f inverse x is cos h inverse x. Okay. This is one way, or you can do like this also. Understood,
Mm.
no? Now try to do derivative of this one, sin h inverse u,
Sin h inverse u.
or sin h inverse x. Just to be easier, sin h inverse x.
Okay.
Sin hy equals to x, right? If you do differentiation, what will happen? Cos hy dy by dx equals to 1, right?
Yes, sir.
So dy by dx will become what? 1 by cos hy, right? But we
Mm.
know cos square hy minus sin h square y equals to 1. So what does that mean? Cos hy is under root 1 plus sin h square y. Agreed?
Mm.
And what is this? What is sin hy? Sin hy is actually equal to x. So under root 1 plus x square. Agreed, ma?
Yes, sir. I'm
So
getting
derivative,
it.
you got the same thing, no?
Yes, sir.
Okay, d by dx of sin h inverse x is equal to 1 by under root 1 plus x square. What does this mean? Automatically, integral of this thing is actually equal to this thing. Okay? So, or otherwise it becomes very difficult for you, right? For us, if you don't, how to exactly do we integrate this? Okay?
Mm.
This becomes very tricky. That's why we need this. Okay, we need all these derivatives because we need it for integrals. Okay?
Mm.
This makes it very easy. So, for example, integral of 1 plus x square you can do very easily, or 1 minus x square you can do very easily, right?
Mm.
Agreed, ma?
Yes, sir.
Integral of 1 by 1 plus x you can do easily. You'll just take logarithm, right? But if you just put a square root, it becomes very tricky. Okay, that's why we are doing this. Okay. Similarly, can you do this for one of this? Tan h inverse x. Tan h inverse x. H inverse x equals to y. Okay, tan hy equals to x. Now do the differential and see whether you are getting this or not. 1 by
Yes.
1 minus x square is what you should get.
Okay.
Okay. Tan inverse x, we got what? 1 by 1 plus x square. Right. You remember that, no?
Mm.
You should remember all of this. All
Like
derivatives of
there
trigonometry.
we used mod so that your entire value wouldn't go negative, right?
Which one, ma?
For sec. Wait. No, sir, nothing.
In trigonometric, regular trigonometric functions, no. So regular trigonometric functions, we for inverse functions also we did derivatives, but we were little careful in saying that the derivative that we were getting should be positive, negative, etc. depending on the graph, right?
Hmm.
Some cases we put a mod so that the slope is positive, right? For secant inverse, right? I think you are talking about secant inverse.
Mm-hmm. Yes, sir.
Because the slope is positive, we included a mod to make the slope positive, right?
Hmm.
So here also we'll be little careful. One thing we are directly doing derivatives here, but we'll be little careful while looking at the graph and say, okay, the slope should be positive, negative, etc. Okay. Or for example, see, sin h inverse, we are getting a positive number, right?
Hmm.
Which is as per our expectation also. Sin h inverse, the slope is always positive. Agreed?
Hmm.
Cos h inverse, the slope is always positive. This also we should get a positive number. Secant h inverse, you should always get a negative number. Okay. Let's see, you
Okay.
are getting secant h inverse negative or not. Secant h inverse, you are getting a negative number. See,
So why
use a
no
positive
mod?
number. This is a negative of some positive number. Okay.
Hmm. That's why they didn't keep mod.
Here, that's why they didn't keep mod because u is anyway between 0 and 1. Right. Secant
Hmm.
h inverse u. Okay. Secant h inverse u. Where is that? Secant h inverse u, which is this one.
Yes, sir.
Secant h x is this one. Secant h inverse u. So what does that mean? It will take inputs of only these numbers only, right? It
Hmm.
will take input only between 0 and 1. Okay, agreed. The
Yes, sir.
domain of secant h inverse is actually between 0 and 1. Okay, so and the slope is always negative. Okay, because x is anyway positive, they didn't put any mod there. Okay, the slope is actually becoming negative. What about cosecant h? So secant h, the graph is only in the quadrant 1. Here it becomes a little tricky. Okay,
Hmm.
see,
Yes, yes.
the cos h inverse, the graph is in both quadrant 1 and quadrant 3, right?
Hmm.
Agreed. Where is this cos h inverse? Cos h inverse is both in quadrant 1 and quadrant 3. Okay, and what about the slope? The slope is always negative, right?
Wait. Yes, sir.
Slope is always negative. So, to make the slope negative, where is this? To make the slope negative, we are putting this mod x here
Mod.
so that this becomes negative here if x is greater than 0, and
Hmm.
if x is less than 0, then also it is negative. Okay, you are forcibly making this one positive, no? So then also it is negative. Agreed.
Hmm. Yes, sir.
Okay, so that's why we are little careful here also. Suddenly, why you got mod? Because otherwise, if you do a differentiation, you will never get a mod, right? The
Hmm.
formula of differentiation doesn't involve a mod.
Understood, sir.
Agreed. Agreed. So basically, what we are doing differentiation of the positive thing one side and negative thing one side. Okay. When x
Yes,
greater
yes.
than 0, this is actually a different differential. Okay. So because the function is not continuous, no? This
Hmm.
we are looking at this as a separate function. We are looking this as a separate function. Okay.
Hmm.
We are not
Yes.
completely doing the differential. We are doing differentiation of this because it is differentiable in this space only. Okay, the overall function is not differentiable continuously. No, at 0
Hmm.
we cannot differentiate, right?
Yes,
Okay,
yes.
what we are doing, we are differentiating this function and got some result. We differentiated this function and got some other result, and we realized both are more or less same. Just that one negative sign is disturbing. So that's why we included both of them in a single result. Okay.
Hmm.
Otherwise, what this means, this derivative and this derivative doing separately, because at x equals to 0, we have to stop, right? This we cannot continue. This is valid only till this part. This is valid only this part. Okay, ma? And
Hmm.
because we got the result and because they are matching, we are combining both of them here. Okay, basically this means this is actually two results. U greater than 0 is one result, U less than 0 is another result. Okay, just like mod x, we are doing differently, right? Okay, what is differential of mod x? Then you say it is 1 when x greater than 0 and it is minus 1 when x less than 0, right? Mod x, the slope.
Hmm.
When x greater than 0, the slope is 1. X less than 0, it is minus 1.
Okay, sir.
Okay, we are telling this separately, right? Similarly, here also it is separate just because uh, it is easier, we are putting it this way. Okay, so now you know how to differentiate all of this. Okay, ma?
Yes, sir.
You'll be able to differentiate now?
Hmm. I do
Okay,
it, sir. But not
very
that.
good. But please do. Okay. After the class, what you have to do? You have to from first
Hmm.
principles. What are the first principles? There
Separate
are
money.
only two formulas, nothing else.
Hmm.
We did everything with the definition of sin hx and definition of cos hx. Okay. E
Hmm.
power x plus e power minus x by 2 is cos h. E power x minus e power minus x by 2 is sin x. With only those two, you should be able to achieve all of this. We did not do anything else, right?
Yes, sir.
We started with only these two, this and this. Okay? So you should be able to do all of this using only these two. Drawing graphs and finding inverses and then establishing identities, doing derivatives and formulas for derivatives, integrals, inverse functions, everything using only those two. Nothing else. Okay, ma?
Hmm. Yes, sir.
Okay, so we have done derivatives of this one also. So automatically, what does means? What does that mean? We know the antiderivatives of this. What does that mean? Integral of this is this sin h inverse x. Integral of this is this. Okay. Now, okay. Now, just for the sake of comparison, I have put all of them together. Okay. You remember you did derivative of this, right? Sin inverse x 1 by under root 1 minus x square you got, right?
Yes, sir.
Okay, so now for sin h inverse, what you have got? You have got plus,
Hmm.
just for comparison.
Yes, sir.
Both are not exactly related, but both kind of resemble each other. Okay, ma?
Hmm.
Okay, here cos inverse minus 1 by under root 1 minus u square. Okay, so whenever we are talking about cos inverse, sin inverse, what should immediately strike you is the graph, and this is negative. Okay, just like when you talk about sin x graph, we will immediately recollect, no? Similarly, all these graphs you should be able to recollect. All these graphs you should be able to recollect. All the derivatives you should be able to recollect. Okay.
Hmm.
These ones are very important. See, here tan inverse what is become 1 by 1 plus u x square. Here 1 by 1 minus x square. Okay.
Hmm.
Note the difference. There is a square root here. Okay. Integral of 1 by under root 1 minus x square is sin inverse. But without the square root, it is actually tan h inverse.
Okay.
Okay.
Yes, sir.
And please note, the derivative of these two are same. What is the difference?
Derivative of cot and
Cot h inverse and tan h inverse are same. Here also they are same.
hmm.
Here they are slightly different. Here they are actually same. Okay.
Hmm.
But we are doing this adjustment in terms of x. Okay.
Hmm.
See, tan h inverse. We have said that tan h graph. You remember tan h and cot hx. Tan h it can go between minus one and one. Okay. Cot h is the other way between infinity to 1 minus infinity to minus 1. Okay. Now, if you look at the inverse graphs, okay, where is the inverse graph? Tan h inverse, tan h inverse. This is between minus 1 and 1, right? The domain is between minus 1 and 1. So, tan h inverse, it will take x values between minus 1 and 1. Okay, whereas cot h inverse x, it will take x values between before this and after this. Okay.
Hmm. Yes,
Okay,
sir.
the x is before minus 1 and after plus 1. Here the x is between minus 1 and 1. Okay. So, though both the function derivatives are same, the results are different. Okay. This is between uh, mod u less than 1 means what does that mean? It is between minus 1 and 1.
Minus one and
Okay.
one. Yes,
This
sir.
is greater than 1 or less than minus 1. Okay. Don't get confused. Though the formulas are same, the results are different. Okay, Amma?
Yes, sir.
Secant h inverse, you remember, the domain is between 0 and 1. Okay. Cosecant h inverse, everything except 0. Okay.
Hmm.
These are the derivatives of inverse trigonometric functions. Okay.
Yes, sir.
Okay. Now, coming to biparts, there is one very important way of integration. Okay. This is called biparts. Okay. Biparts has got, let's say there is an integral like x e power x. Okay.
Hmm.
X e power x. We know integral of x, we know integral of e power x. Right? We know both of them. But together, how do we do? that is a big problem, right? If there is a differential, you can easily do this one. If you have to derivative of x equal x, what you will do? You will keep the first function, you do differentiation of the second function, etc., etc. Right?
Hmm.
Now, similarly, here what we do, we will take one of these functions as first function, another function as second function. Okay? One
Yes, sir.
function as first function, and not necessarily the left one should be first and right one should be the second one. Okay. E power x and x also you might get. E power x into cos square x you might get, whatever. Okay. So we have to be little careful in choosing which function as which, what is the first function, what is the second function. Okay. Generally, what we choose, first function is where differentiation is easy. Okay.
Yes, sir.
Second function where integration is easy. Okay. Of the
Got it.
priority, because integration is difficult. For any function you can anyway differentiate. Okay.
Hmm. Hmm.
So the more important thing is this, not this. Because this one, whether however difficult it is, you will be able to do it. Okay. When I say differentiation easy, what this automatically means, differentiating multiple times. If you differentiate this, so for example, if you take x, if you differentiate this one, if you differentiate this will become 0. Okay.
Hmm. Yes, sir.
Okay, here if you integrate, it will keep on becoming e power x, e power x, e power x. Okay. On
Hmm.
the other hand, if you take the other one, okay, if you take e power x here and x here, okay, if you differentiate this, you'll get e power x. If you integrate x squared by 2, if you integrate this, what will become? X cubed by 6. Okay, x power 4 by 24 or something, right?
Hmm.
Okay, so here if you see, the integration become complex and complex. Agreed.
Yes, sir.
So, for example, if there is a function like 2x plus 1 into e power x, okay, here you can clearly see. If you put this as second function and this as first function, this function if you keep on integrating, it is getting bigger and bigger. Okay, ma.
Hmm.
Okay, it is getting bigger and bigger. This one is constant. So ideally, getting bigger becomes a little tricky for us. Okay. So, for
Hmm.
example, or e power x into tan x. Okay. If you integrate tan x, you will get, yesterday did no log of secant x or something. If you try to integrate, if you try to integrate this, we don't know what exactly how to integrate log of secant x, right? It becomes a struggle for us. Okay.
Hmm.
Whereas if you take this function here and this function here, the integrate you can do as many times. And differentiate also you can do freely. Okay.
Yes, sir.
Agreed. So how do we choose? You choose first function as a second function as the one where you can do integration easily, and first function as the other function. Basically, our first function differentiation should be easy. Second function integration should be easy. Okay. Now let's obviously in this case what you will do? Second function as e power x, first function as x. Okay. Now let's do derivative. This is 1. Okay. Let's do integration. This is e power x. Okay. Integration by parts of this thing tells us what exactly is the this thing, x into e power x. Okay. Minus of integral of this 1 into e power x. Understood?
Hmm.
Okay. So basically what you have done taken two functions, called it the first function and second function. Okay. First function you keep you differentiated. Second function you integrated. Okay. Then what is the result? Integral of this thing is first function into second function minus integral of derivative of first function into integral of second function. Understood, no?
Yes, sir.
Now, so here this integral we have expressed in some other integral. Okay. We did not do the complete integration. Right. This integral,
Hmm.
what you have done, this into this minus again integral of this into this. Okay. So basically this integral we have expressed in some other integral, but here luckily, see, we are able to remove this x from this integral. Okay.
Hmm.
We have simplified this. This one we know, e power x, right? So basically x e power x minus e power x, right?
Hmm.
This one we
Yes, sir.
know. So basically the answer is this one. Now you can now just try doing differentiation of this. Are you getting this or not? x e power x, if you do differentiation, what will happen? X into e power x plus x, right?
Hmm. Yes, sir.
X into e power x minus e power x. Wait, x into e power x plus e power x, sorry, right?
Hmm.
X into e power x plus e power x into differentiation of x, which is 1, this one. So you both will get cancelled, you will get x e power x. Okay. So just by looking at this, if you are able to imagine that this would be the solution, that is wonderful. Okay. In some cases, you will be able to do this. Okay. For example, if you are given something like this, sin x dx, you can easily imagine what will I do if I take minus cos x, if I differentiate, I will get sin x. You can imagine that, right? If you are able to imagine what exactly is that could be that function, that is wonderful. Or otherwise, we will use this kind of method. What is this method? This is called by parts. Okay, what we are doing? We are doing the integration by parts. First we have done this one, and we have simplified this one, and we have got this one. Agreed, ma?
Hmm. Yes, sir.
Okay. What is integration by parts? Now tell me what is the formula?
Integration by parts.
Integration from function f, and there is function g, and there is dx. Okay. What you do, let's say f is the first function and g is the second function. Okay, you differentiate this and you integrate this one. Okay, you integrate this one, whatever. Okay,
Sir,
now
in college, what we taught was integral of UDV, that thing.
okay, integral of u dv equals to uv
U
minus integral of v du. Okay,
that is also the same thing, right, sir?
this is the same thing. Okay,
Hmm.
now integral of u dv. Okay,
Yes.
integral of u dv is integral of uv. Okay, uh, uv minus integral of v du, right?
Hmm. Yes, sir.
Okay, so here what he has done, there is a function, there is a function. Okay, dv is also function, right?
Yes, sir.
Okay, okay, then what he has done, uh, he has done derivative of u. What will that become? Du. Agreed?
Hmm.
Okay, he has done integral of dv. What will that become? V, right?
Yes, sir.
Now what he has done, uv minus integral of this into this, du into v, which is nothing but integral of v du, uv minus v du. What is this? Integral of u dv. Understood?
Okay, sir.
Understood. He has taken first function as u and second function as dv.
Understood.
Okay. Okay. So now, so for example, let's take the same case, x e power x dx. Okay.
Hmm.
Now, e power x dx, he has taken the second function. First function is x. Okay.
Understood.
So, first function and the integral of e power x dx, what he has got? E power x. Okay. That is this one. E power x minus integral of what is v?
Sir?
What is v? See, here we have got dv as e power x dx. What is v? V is e power x, right?
Hmm.
Okay. E power x. What is du? X equals to u. Du is dx
X.
equals du is dx. Okay.
Okay, sir.
Du by dx equals to 1. Okay. Don't get
Hmm.
confused. Du is equals to dx. So that's why we are getting this. Okay. Again, you have got e power x minus e power x. X e power x minus e power x.
Hmm.
Okay, ma? So both
Okay.
are same. Both are same. Whether you do it like this and minus this, or you do it like this, then also it is same. Okay. So then what this function says is, you'll take this part as entirely as dv. Okay.
Understood.
He'll take this entire part as dv. Okay. What I have told, you just integrate this thing, and you put a dx additionally. Okay. Or otherwise, if you do this also, it is still fine. Okay, ma?
Hmm.
Okay,
Okay.
so now how we got this? Let's say there are two functions, f of x into g of x. Okay, if you're doing derivative of this, what is this? F of x into z dash x, agreed?
Hmm. Yes, sir.
Plus g of x into f dash x, agreed?
Hmm.
Okay, so this is this, right? What does that mean? If you integrate this one, you should get this one, right? Integral of f of x g dash x, because this is kind of antiderivative, right? G of
Hmm.
x into f dash x. Okay, you are integrating all of this with respect to dx equals to what? If you integrate this, you should get f of x into g of x.
Hmm.
Agreed? So
Yes, sir.
basically d of this thing equals to this times dx. We are just integrating on both sides. Okay.
Hmm.
Now this one f of x g dash x dx plus integral of g of x f dash x dx. Agreed, ma?
Yes, sir.
Equals to what? F of x g of x. Okay. Now if you call f of x as u, g of x as v. Okay.
Yes, sir.
Okay. Now dv by dx will become what? G dash x dx. Agreed?
Yes, sir.
G dash x. Okay, okay. dv by dx is g dash x.
Hmm.
Okay, our dv is g dash x dx. Agreed?
Yes, sir.
dv is what? dv by dx is g dash x. dv is what? G dash x dx. Agreed?
Hmm.
So
Yes.
what is this one? G dash x dx. This is dv. Okay.
Hmm.
What is f of x? This is u. Okay.
Okay.
Integral of u dv uh, plus uh, this one. What is f dash x dx? du is what? F dash x dx only, no?
Yes, sir.
Agreed. If u is f of x, what is du? F dash x dx. This
DX.
means what? This is du. What is g of x? This is v. Right?
Hmm.
Plus integral of v du equals uv. Okay. What does that mean? Integral of u dv becomes uv minus, we are taking this one to this side, v du. This is the
Yes.
proof of integration by parts. Okay, ma? What
Understood.
did we do? We did nothing. This is again antiderivative only, right? What we
Hmm.
have done? We have done UV function. We have taken two functions, product of two functions. We did derivative of that. Okay?
Yes.
And then we use that antiderivative again. What we have done? When we integrate this, we should get this. This is what we are saying. There is a product of two functions. If we differentiate, if you get this, that means if you integrate this, you should get this. Okay? That's what we have
Understood.
done. If you integrate this, you should get this one. Okay? Now we are calling this one as u, this one as v. Okay?
Hmm.
And what does that mean? This one, we are just split this integration. G, if this is v, g dot x dx will become dv, right? dv by
Hmm.
dx is, agreed.
Yes, sir.
If v equals to gx, v equals to g of x, what does that mean? dv by dx equals to g dash x, right?
Hmm.
Which is nothing but dv equals to g dash x dx. So we express this as dv and f of x is anyway u. And what about f dash x dx? That is obviously du. Okay, v du. So integral of u dv plus integral v dv is what? uv. So obviously that means integral of u dv equals to uv minus integral v du. Okay. So now the important thing here is you'll be given a function like this. Okay. So for example, x square e power x dx integral. Okay. Now
Hmm.
this entire piece you should be able to take it as dv. dv equals e power x dx. What does that mean? What is your v? V is e power x then. Agreed, ma?
Yes, sir.
So this entire piece you have to take together. When if you are choosing this format, you should be able to take this entire piece. In some other textbooks, what you will see, integral of first function into differential of second function minus integral of derivative of first function into second function, something something. You will see some similar kind of formula. Okay,
Hmm.
understood. Both mean the same thing. So your book would have given this. Okay, some books would give some other formula. Okay, integral of first function into derivative of second function. Okay, minus integral of derivative of first into integral of second, something like that. Okay, both mean the same thing. Okay, but the trick here is you should be able to choose which function as the first one and which one as the second one. Okay, the second one should be, you should be able to do integration easily. Understood, ma?
Yes.
Okay, so now you will be able to do these integrations also. For example, where these functions derivative, individually, if you should be able to do. Okay,
Hmm.
because what this is doing, this is actually breaking that into a simpler parts. Okay,
Okay,
individually, if you should be able to do. Now try to do some more questions on using integration by parts also.
okay, sir.
Okay. Now, did you do, then I think later we'll be able to do reduction formulas. So, for example, tan nx, sin nx, whatever. So,
Hmm.
how exactly do you use by parts to reduce these ones to simpler ones? So, basically, here what you have done, here we have reduced a complex function to a simple one, right? So, this technique is very useful. Lot of complex functions will reduce to simpler ones to do integration. Okay,
Okay.
ma? Okay, cool.
Hmm.
So please do some questions on this thing.
Okay, sir.
Okay, some these by parts questions, and at the same time do all these derivatives of hyperbolics once again. So,
Fine.
so at the click, you should be able to immediately recognize whenever you get a function like this, whether this is this, whatever. All
Hmm.
derivatives and all integrals of all trigonometric and hyperbolic functions. Okay, ma?
Fine, sir.
Okay, then.
Thank you, sir.
Okay, ma. Take care then. Bye bye.
Hmm. Sir.